So our next set of theorems all to do with angles. The first one, the one we sort of looked at yesterday in our definitions, for the angle subtended by an arc or a chord at the centre is double the angle subtended by the arc or the chord at the circumference. There's our diagram. So AOC twice ABC. As I mentioned yesterday, I tend to say subtended by the arc rather than the chord, because if I just draw in a chord, I could go in any direction. But basically, if you do say chord, you just got to make sure they're subtended in the same direction. Okay. Let's prove it. Well, what I'm going to do is I will draw in a line, or an interval, BO, and I'll produce that through to another point X. Now, we know triangle AOB is isosceles, because we've got two equal radii there. So therefore I know OBA and OAB would be the same size. Well, AOX is the exterior angle of triangle OAB. So I know they'll add together to give OBA plus OAB. Therefore, OAX is twice OBA. Now, of course, I could do exactly the same thing with triangle BOC. Now, I don't go through that whole proof again because it would be exactly the same proof. I'll just say, well, angle COX would be twice OBC using a similar method. Well, AOX and COX add together to give AOC, and OBA and OBC add together to give ABC, so AOC is twice ABC. Okay, now from that comes the next theorem about the angle in the semicircle being a right angle. A very easy one to prove, because now I can use the angle at the centre being twice the angle at the circumference. Now we know the angle at the centre, AOB, is a straight angle because it's a diameter. So it's 180. Well, therefore, we know AOB is twice ACB. So ACB must be 90 degrees. So the angle in the semicircle will always be 90 degrees. Voila.